the specific points in space that were connected by edges and faces. Being able to describe something completely with a limited amount of information is called discrete measurement. With discrete measurement, points are located at specific locations in space, and the distances between them are connected with straight lines. The direction of the overall line will only change at the specific points. This means that a simple discrete line will never be able to measure the length of a curve. Even if the points were located very close together, the straight lines between them would still take shortcuts across the curve. The only way to reproduce the correct length is to abandon discrete measurement and use calculus to envision the points on the line as being separated by zero distance. The same principles apply to surfaces. The area of a smoothly curved surface can be approximated with a discrete mesh. The discrete points are now connected by straight lines and flat planes. Adding in more points to a mesh can give a better approximation, but the flat planes will never reproduce the curved area. To do this, one must again abandon the discrete and turn to calculus. However, just because a mesh is crunched so that its points are separated by zero distance doesn't necessarily mean that it will accurately estimate a curved shape. For instance, we can start with a cylinder again and make a rough approximation of the surface area with a polygonal mesh made of triangles called a Schwartz lantern. This mesh is obviously too rough, and we will need to add more sample points to get a better approximation. There are two ways we can increase the amount of samples in this polygonal mesh. We can increase the number of triangles around the cylinder, or the number of triangles down the height of the cylinder. Increasing the triangles around the cylinder will smooth out the mesh, and we will eventually get an accurate calculation of the surface area. However, if we increase the number of triangles along the height of the cylinder, the mesh begins to zigzag. Adding more triangles vertically causes the mesh to crinkle more and more as it folds up like an accordion. In this way, the surface area actually becomes larger and larger and extends infinitely past the area of the original cylinder. This may appear obvious since we can see the folds developing. But when we increase the number of triangles vertically, as well as the number of triangles around at the same rate, we appear to get a correct approximation. However, the appearance is misleading because we still have created folds like before. Although the crinkles are now quite small, they are still present. Depending on how we increase the resolution, the resulting estimation might look accurate, but could give us a value anywhere between the actual area of the cylinder and infinity. Even if a mesh appears to give us a good approximation, we have to know its limiting behavior. Infinitely small meshes don't necessarily give us correct answers. It seems that in a world of continuously changing values, discrete measurement is only able to provide broken, chunky samples. So what good is discrete measurement at all? Why would mathematicians ever want to employ a discrete model to understand something that is infinitely changing? Discrete math, this seemingly oversimplified view of the world, got its biggest boost from, oddly enough, the invention of the most advanced calculation tool, the computer. Computers, with all their power, can only think about objects in terms of finite